Ever since the first studies of the Great Pyramid in Egypt have been made, researchers have been amazed at the mathematical knowledge that is encoded into the Great Pyramid, the measurements that are used in it. Even the placement of the Great Pyramid has aroused great interest among Egyptologists.
On the Giza Plateau, beneath the relentless Egyptian sun, there is a place where the Great Pyramid seems to reveal a secret about itself. Deep inside the monument, above the chamber we call the King's Chamber, are 5 enormous layers of granite beams stacked one above another. They are not decorated like the walls of a royal tomb. There are no treasures waiting between them, no inscriptions explaining why they are there, no ancient engineer standing beside them to tell us what he was thinking. There is only stone. Massive granite blocks, some weighing many tons, were transported from quarries hundreds of kilometers away and raised deep into a structure that would eventually contain millions of tons of material. Some of the beams are cracked, their surfaces carrying scars left by stresses that occurred thousands of years ago. Yet the chamber below survived, and the pyramid survived with it. For more than 4 millennia, the monument has endured earthquakes, weather, political collapse, changing civilizations, and the disappearance of the people who built it. And still, when modern engineers look at those beams, the same question remains. What exactly were the ancient builders trying to protect? And how did they know how much strength the structure would require? To understand why that question matters, we have to step backward, away from the pyramid itself and into the history of measurement. For most of human history, a monument like Giza could only be understood through the limits of human senses. A person could look at a wall, measure it with a rope, calculate an angle, study the stars, and record the results on papyrus or stone. But every measurement depended on the observer. Every calculation had to be repeated by hand. Every mistake could disappear into the process. Then, in the 19th century, the world entered a technological revolution that changed the relationship between human beings and information. One of the men standing at the center of that revolution was Thomas Edison. Edison was not an Egyptologist, and there is no credible evidence that he possessed some hidden explanation for the Great Pyramid. His importance to this story is something else. He helped popularize a new technological philosophy. Instead of relying entirely on human perception, build machines that can capture, record, reproduce, and analyze phenomena beyond the limits of ordinary observation. When Edison worked with sound recording, electricity, telegraphy, and other emerging technologies, he was part of a generation that began turning invisible events into measurable information. A sound that once vanished into the air could suddenly be recorded. An electrical signal that existed for only an instant could be captured and studied. The world was becoming something that could be measured, stored, compared, and analyzed. More than a century later, that philosophy has reached an extraordinary destination. Today, we can point laser scanners at the Great Pyramid and convert its surfaces into billions of measurements. We can reconstruct chambers digitally. We can record the exact angles of passages, the dimensions of walls, the orientation of the monument, and the relationships between spaces hidden deep inside the stone. In a sense, Edison helped usher in the age of machines that extend human senses. The researchers examining Giza today are using the descendants of that same idea. Only now, the machines do not merely record what we can see. They can search through enormous quantities of information for patterns that no individual human could realistically examine. And that is where the modern mystery begins. Imagine taking the complete digital record of the Great Pyramid, every survey, every internal measurement, every known chamber, shaft, passage, angle, alignment, and structural dimension, and placing it into a powerful analytical system. Instead of telling the system what answer to find, the researchers give it a much simpler instruction. Look for patterns. Do not assume the pyramid was built according to one particular theory. Do not assume every proportion was intentional. Do not assume the ancient Egyptians possessed knowledge beyond what archaeology can demonstrate. Simply compare the numbers and identify relationships worth investigating. That distinction is crucial because a machine finding a correlation does not automatically prove that the ancient builders intended it. A mathematical pattern can be meaningful, accidental, or created by the way modern researchers choose what to measure. But if a pattern survives independent measurements and archaeological scrutiny, it can become something much more interesting. A question that deserves to be investigated. Before we can understand what such a system might find, however, we have to confront the conventional story of the pyramid. Around 2560 BCE, during the reign of Pharaoh Khufu, an enormous organized workforce assembled at Giza. Contrary to the popular image of thousands of chained slaves being forced to build a monument, archaeological evidence points toward a complex labor system involving skilled craftsmen, quarry workers, administrators, food producers, transport crews, and seasonal laborers. They were part of a society capable of mobilizing enormous resources for a royal construction project. Limestone was quarried and moved across the Giza Plateau. Granite was transported from the Aswan region far to the south, using the Nile and associated waterways. Heavy blocks could be moved on wooden sledges, dragged by teams of workers, while water may have been poured onto sand to reduce resistance. Stone was shaped using copper tools, pounding stones such as dolerite, abrasives, and techniques developed through generations of practical experience. Slowly, block by block, layer by layer, the pyramid rose above the desert. The result was extraordinary. The Great Pyramid originally stood at roughly 146 meters, crowned with a casing of polished limestone that reflected sunlight across the landscape. Its construction required the organization of millions of individual stone blocks and the coordination of a workforce on a scale few ancient projects could match. For thousands of years, it remained the tallest known human-made structure on Earth. And archaeological discoveries have made one thing increasingly clear. There is no need to invent an unknown civilization to explain who built it. Human beings built the Great Pyramid. Egyptian workers quarried the stone, transported it, shaped it, positioned it, and assembled the monument. We have evidence of their settlements, their food, their tools, their administrative systems, and even graffiti associated with work crews. The remarkable thing is not that humans built Giza. The remarkable thing is what those humans were capable of achieving with the technology available to them. Because the deeper researchers look, the more the word precision begins to dominate the story. It is one thing to create a massive pile of stone. It is something entirely different to create a structure whose foundation, orientation, geometry, and internal architecture demonstrate such extraordinary consistency. The base covers roughly 13 acres, and although it is not mathematically perfect, it is remarkably level across an enormous footprint. Modern surveyors can identify variations, but the overall achievement remains impressive. The ancient builders did not have laser levels or satellite positioning. They had water, plumb lines, sighting instruments, ropes, careful observation, and an understanding of practical geometry. A horizontal water surface can establish a level reference. A straight line can be established by tensioning a cord. Repeated measurements can reduce errors. The tools were simple, but simple tools do not necessarily produce simple results when used by specialists who have spent generations mastering them. Then there is the orientation. The four sides of the Great Pyramid are remarkably close to the cardinal directions. The deviation from true north is only a few arc minutes, depending on the method used to calculate it. That is an astonishing achievement for a civilization without a magnetic compass. But again, the ancient Egyptians had another instrument available to them: the sky. The stars provided a celestial reference system. By observing stars and their apparent movement across the night sky, ancient surveyors could establish north with considerable accuracy. The heavens became their compass. The earth rotated beneath a predictable sky, and the builders could use that predictable movement to establish orientation on the ground. Suddenly, the pyramid's alignment does not require mysterious technology. It requires something arguably more impressive: patience, astronomical observation, mathematics, and the willingness to repeat a measurement until the result was good enough. And then there are the stones themselves. The original casing stones were cut from fine limestone and fitted across the pyramid's exterior with remarkable care. Inside, the granite is even more demanding. Granite is hard, abrasive, and difficult to shape, particularly when the available metal tools are relatively soft. But the ancient Egyptians did not need copper alone to do all the work. They could use harder stone tools for pounding and employ abrasive materials to wear away granite gradually. It was a slow process, but the Great Pyramid was not built quickly. Decades of organized labor provided something modern observers sometimes forget: time. If one worker can remove only a tiny amount of material in a day, thousands of workers repeating the process over years can accomplish an enormous amount. Ancient engineering was often a battle between force and patience, and the Egyptians possessed both. The relieving chambers above the king's chamber bring all of these questions together. Their purpose is generally understood in structural terms. They help distribute the enormous weight of the pyramid above the chamber and reduce the pressure concentrated directly over the room. But the scale of the construction is still astonishing. Massive granite beams had to be transported from the south, moved across the construction site, raised into position, and integrated into the pyramid as the structure rose. The builders were effectively creating a protective system above a chamber buried beneath an enormous mountain of stone. They could not run a modern computer simulation of the stresses. They could not place sensors inside the granite. They could not consult a modern structural engineer. They had to rely on accumulated knowledge, practical experience, geometry, and observation. And perhaps that is the most important connection to the technological revolution that began with people like Edison. The difference between the ancient builders and modern researchers is not that one side possessed intelligence and the other did not. The difference is the instruments available to them. The builders of Giza had to solve physical problems with their hands, eyes, ropes, stone, water, stars, and memory. Edison and the engineers who followed him developed machines capable of recording phenomena that human senses could not preserve. Today, we have taken that process one step further. We can turn an ancient monument into a digital object and ask machines to examine relationships across millions of measurements. But the machine does not make the past mysterious by itself. It simply gives us a new way of looking. If an algorithm discovers an unusual ratio, that does not mean the Egyptians secretly possessed modern mathematics. If it finds a geometric relationship between two chambers, that does not automatically mean the relationship was intentional. And if it identifies a statistical pattern connecting several ancient structures, archaeologists still have to determine whether the pattern reflects deliberate planning, shared cultural knowledge, similar engineering constraints, or coincidence. The machine can point toward the anomaly. It cannot, by itself, tell us what the ancient builders meant. That is why the Great Pyramid remains so compelling. Every generation arrives believing it has better tools than the generation before it. The Victorians measured the monument with surveying instruments. The 20th century brought photography, archaeology, and increasingly sophisticated structural analysis. The modern era has brought radar, laser scanning, digital reconstruction, and artificial intelligence. Yet the pyramid continues to resist the final word, not because it necessarily contains supernatural secrets, but because it represents an engineering achievement so large that even after thousands of years, we are still reconstructing the process by which it was accomplished. Thomas Edison once belonged to a generation that believed the world could be understood by recording what had previously disappeared. The Great Pyramid now sits at the opposite end of that idea. It is something that refused to disappear. It has remained in place while languages vanished, kingdoms collapsed, technologies changed, and civilizations rose and fell around it. The people who built it are gone, but their decisions remain frozen in stone. A misplaced block, a carefully aligned wall, a precisely cut joint, a massive granite beam, a corridor pointing through the darkness. Every one of these is a piece of information. And perhaps that is the real story of Giza. Not that an unknown power built something impossible, but that ordinary human beings, working with extraordinary discipline, created something so ambitious that it continues to challenge the machines of a civilization thousands of years younger. The pyramid does not need a lost super-civilization to make it astonishing. It only needs us to recognize what ancient people were actually capable of. And now, with the same technological philosophy that began transforming the modern world in Edison's era, we are finally able to measure the monument in ways its builders could never have imagined. The question is no longer simply, how did they build it? The question has become something much more interesting. How much did they know? Because every new scan, every new measurement, and every new analysis gives us another opportunity to look at the same ancient stones and discover that the people who built them may have understood their world far more deeply than we once assumed. But this is where the story takes a turn. Each of these facts, examined by itself, can be explained. The extraordinary flatness of the foundation can be attributed to patient surveying. The alignment can be explained through astronomical observation. The precision of the stonework can be attributed to generations of skilled craftsmen, specialized tools, abrasive techniques, and an enormous workforce operating over decades. None of these explanations requires anything supernatural. In fact, that is precisely what makes the Great Pyramid so fascinating. The conventional explanation works remarkably well when each feature is examined independently. But what happens when you stop examining the anomalies one at a time and begin looking at all of them simultaneously? What happens when the measurements become too numerous for a single human mind to compare, and the monument becomes not simply a building, but an enormous mathematical data set? That question leads directly into the modern age of computation. Thomas Edison helped establish a philosophy that would eventually transform science and engineering. Record the phenomenon, preserve the information, and then examine it repeatedly until the hidden behavior becomes visible. Edison could not have imagined laser scanning or artificial intelligence, but the principle is surprisingly similar. A machine can preserve information that human memory cannot. It can compare measurements without becoming tired. It can repeat the same calculation thousands or millions of times without losing concentration. And today, when researchers examine the Great Pyramid, they possess something ancient engineers never could have imagined: a digital representation of the monument detailed enough to allow computers to compare dimensions, angles, orientations, and proportions simultaneously. So imagine the researchers gathering everything they could: the internal geometry mapped with modern surveying equipment, the dimensions of chambers and passages, the slopes of corridors, the orientation of the pyramid relative to true north, the relationship between its height and its base, the volume of stone, the position of individual structural features, astronomical alignments proposed by researchers over generations, measurements gathered not from a single expedition, but from centuries of observation. Instead of asking a computer to prove a theory, they give it the opposite instruction. Find the relationships, identify the patterns, tell us what appears unusual, but do not assume in advance what the answer should be. And then, according to the scenario being examined, the system produces its first major observation. It begins with a number hidden inside the basic proportions of the monument. The relationship between the pyramid's height and the perimeter of its base produces a value remarkably close to pi. The famous mathematical constant describing the relationship between the circumference of a circle and its diameter appears naturally when the dimensions of the Great Pyramid are compared in a particular way. This observation is not new. Researchers and enthusiasts have discussed the pyramid's relationship with pi for more than a century. What changes in the modern story is not the existence of the calculation, but the ability of computational systems to compare it with thousands of other measurements at the same time. And here, the documentary has to slow down, because this is exactly where a fascinating mathematical observation can become misleading if we are not careful. The Great Pyramid does not contain a written mathematical statement saying, "This is pi." The ancient Egyptians did have sophisticated practical mathematics, but there is no surviving Old Kingdom document proving that the builders used the modern mathematical concept of pi in the same formal sense that later mathematicians did. The ratio can emerge naturally from the geometry of a pyramid, and ancient construction methods involving circles, ropes, wheels, or repeated measurements could potentially generate relationships involving circular geometry without requiring a formal symbolic understanding of the constant. In other words, the presence of a pi-like ratio is interesting, but it is not by itself evidence of lost advanced mathematics. That distinction, however, does not make the number meaningless. It makes the question better. If the relationship was intentional, how did the builders achieve it? If it emerged naturally from their construction methods, what does that tell us about the practical mathematics they used? And if the ratio appears because of the chosen dimensions rather than deliberate mathematical encoding, why did those dimensions take the form they did? These questions transform the number from a sensational claim into a genuine historical problem. The machine can identify the relationship, but it cannot tell us whether the ancient builders thought of it as a mathematical constant, an engineering consequence, or simply a useful proportion. Then, the analysis moves deeper into the king's chamber itself. The chamber is a remarkably austere space, constructed from enormous granite blocks deep within the pyramid. Its walls, floor, and ceiling form a geometry that has fascinated researchers for generations. When different dimensions are compared, some relationships can resemble another famous mathematical proportion, the golden ratio, often represented by the Greek letter phi. The golden ratio is approximately 1.618, and it appears in numerous mathematical constructions. It is also frequently observed in natural growth patterns and geometric forms. But here again, caution is essential. The golden ratio has become one of the most frequently claimed hidden numbers in architecture, art, nature, and ancient monuments. And not every apparent appearance represents intentional design. Yet suppose, for the sake of the investigation, that multiple independent proportions within the pyramid repeatedly produce values close to well-known mathematical constants. That is when the question becomes more interesting. Not because two numbers automatically prove a secret code, but because researchers can begin testing whether the relationships remain when the measurements are independently repeated. They can calculate how sensitive the result is to small changes in dimensions. They can compare the pyramid against other ancient structures. They can run statistical simulations to estimate how often similar ratios would appear by chance. They can deliberately search for the same patterns in monuments that were not constructed in Egypt. This is where artificial intelligence becomes useful, but also where it can become dangerous. A powerful system can search through enormous numbers of possible relationships, far beyond what a human researcher could reasonably test manually. But that same power means it can discover patterns that have no historical meaning. Give a system enough measurements, and eventually some of them will resemble famous constants. The more relationships you test, the greater the probability that something will look extraordinary. This is a fundamental problem in statistics. If you search long enough, something will eventually appear significant unless you correct for the number of comparisons being made. Edison understood a version of this problem in a very different technological context. His laboratories were filled with experiments, failed prototypes, repeated measurements, and endless attempts to separate useful effects from noise. Invention was not simply about discovering something strange, it was about determining whether the strange result could be reproduced. A single surprising observation was not enough. It had to survive testing. That same principle matters when examining ancient monuments with artificial intelligence. The machine may discover the pattern, but humans still have to determine whether the pattern is real, reproducible, statistically meaningful, and archaeologically plausible. And now the pyramid begins to look different. Instead of seeing isolated measurements, researchers can see relationships between measurements. Instead of asking why one chamber has a particular dimension, they can compare that dimension with the entire geometry of the monument. Instead of examining the orientation of one passage, they can compare it with every other angle in the structure. The pyramid becomes a network of numbers, each measurement connected to dozens of others. A change in one dimension affects another. A small deviation in the foundation can alter an angle. A particular slope can influence the height. A chosen base length can determine the volume. Suddenly, the monument begins to resemble something closer to an enormous engineering system than a simple pile of stones. And that is where the story becomes genuinely compelling. Because even after we remove the sensational claims, the underlying achievement remains astonishing. The ancient builders did not need modern computers to create sophisticated geometry. They needed a system of measurement, standards, skilled craftsmen, and generations of accumulated knowledge. Their mathematics may have been practical rather than abstract, expressed through dimensions, ratios, angles, and construction procedures rather than equations written on a screen. The pyramid itself may have been their calculator. Every stone placed correctly was a physical expression of a measurement. Every aligned wall was a statement about direction. Every carefully cut joint was evidence of a process refined through experience.